sometimes I call him Anand. That's the name that he's popular with all of us. And let us first congratulate him for winning this year's SS Vatnagar Award. And we are really, we can just clap because we are, he's from Calicut. And actually he did his undergraduation from Calicut University. So we are really proud for Anand for winning these things. And we hope that as soon as the situation normalizes, Anand will be here with us. So Anand is a professor at IIT Mumbai, and his main area of research is automorphic forms and representation theory, which is kind of, as you have already had quite a few lectures, is a very, very active area and very interesting area. And we are really privileged to have Anand with us, and hopefully we'll see him soon here. You can spend more time with him. So I'll request Professor Anand to begin his talk.
Okay. So thank you so much. Thank you so much, Kalyan, for the introduction and for the warm welcome, virtual welcome to your campus. Of course, I mean, I see the new students there. I'll say a few words and then start my lecture. As Kalyan already mentioned, I am from Calicut, so I have this close association with this institute. And it's a city where I went to college for 5 years. And so some of the students I may not know because you are new to the place, but the other people there, all of them are my friends, Akhilesh and Pranav and Vijay and Kalyan. So all 4 of them close friends. So I look forward to visiting the place in person very soon. And I hope to see all the students, interact with everybody, etc. And as we were just discussing just before the starting, that the students may not follow each and every word, but it doesn't matter. And I was just telling Pranav that we ourselves don't follow, everything if the lecture is in a slightly different area. So that's in the nature of the subject. It's okay. But we should pick up, a few words and get to know people. It's all part of our math culture. So I will start sharing the screen, my slides. Okay, so I thought my lecture was already here. Yeah. It's visible, no? So I'll make it full screen.
Yes, it's visible.
It's visible, right? So it has become full screen also, right, Pranav?
Yes, it has.
Okay, good. So let's start. The title of today's lecture is Distinguished Representations for Galois Pairs. And the broad topic is representation theory. And there are certain representations called distinguished representations. They can be defined quite easily. You will see the definition in the beginning slide, very easy definition. The moment you know what a representation is, this can be defined. So we will do that, and then I will not get into many technical details, but I will give a broad survey of the topic. So happy to be part of this conference, especially because the name of Srinivasa Ramanujan is also involved, and as you know, tomorrow is the National Mathematics Day, when the conference is ending, appropriately with a talk of Professor Ramurthy on Ramanujan graphs. So this work is joint work with Nadir Matranj, who's in France, University of Poitiers, and Dipendra Prasad, who's here in Bombay, in Mumbai. Okay, so let me start with this beautiful picture that I like a lot, which I don't think so. I was there beginning of this year. In fact, Akhilesh organized this wonderful conference end of Jan 2020. And I think that was the last last trip that I had. And after that, I have not been outside Mumbai. So this photo is from long ago. I visit KSOM very frequently. And most of the students also must have discovered this place already. This is my favorite place inside KSOM building. So there is a blackboard that you see. Opposite, there's also a whiteboard, I guess. And you can see the beautiful hilly region. Okay, so look forward to being in this place very soon. This is where we take our coffee. Okay, so let's start. We will introduce the notion of a distinguished representation, and I'm going to do it in three settings, three flavors. One for finite groups, which means basically I will be taking groups like GL2 or GLN matrix groups over finite fields. Those will be my finite groups. And this part should be the easiest because after all, we are discussing finite groups. And then there are these fields called periodic fields, field of periodic numbers and finite extensions of that field. So that is what we call local fields. And it can be described in the local setting. And there's also the global setting by which one means number fields. So what is a number field? It's an example is the field of rational numbers or finite extensions of the field of rational numbers. So you know all these objects. You know rational numbers. You can take finite degree extensions of rational numbers. So those are the number fields. And you can complete a Q, the field of rational numbers, with a periodic metric, periodic norm, and that is what is called QP, a periodic field. A finite extension of QP is also called a periodic field, and then you have finite fields, which you know very well. And I will define this notion in all these settings, and I will in particular give the notion of what is called a generic representation, which is a particular case of distinction for a particular pair. We will see that soon. And then we will recall some of the results for GLN. So GLN over a field is the group of all n by n invertible matrices. N by n matrices with determinant not equal to 0, they form a group. And that is the most well understood group in this theory. And we will recall some of the results. And towards the end stage, some of the new results, and that will be where we end the talk. And that is on the group SLN. So this is a subgroup of GLN with determinant equal to 1. GLN is determinant non-zero, SLN is determinant equal to 1. And it's a bit subtler there. And that's where the new results are there. So SLN case is a bit subtler, a bit harder. Due to the presence of so-called L packets. I will not define it, but I will illustrate what the complication is towards the end of the talk. The basic point is that instead of studying one representation, it is more natural in what is called the Langlands program in number theory to study a group of representations together, a packet of representations together, what is called L packet, L for Langlands. We probe for distinction. So I'm going to introduce this notion, and we probe for distinction inside an L packet in terms of this notion that I'm going to introduce, which is genericity. So let's start with finite groups. So what you have is a finite group G. I'm not even saying GLN, FQ or anything, any subgroup, any finite group G. And consider any subgroup H of G. The notion is so easy to define, so we can define it in this generality. So take a finite group and take a subgroup, and let pi be an irreducible representation of G. So those of the MSc students who might not have seen this, what this basically means is you have a homomorphism of G. So all my representations are over vector spaces over complex numbers. So basically what this means is there is a homomorphism from this group to another group, and that group is GLNC, n by n matrices, invertible matrices with complex entries for some n. Okay, that's all that this means. And irreducible is meaning it's one of the basic representations. There's no sub-representation. So start with this data. What you have is a representation of the big group G, and also what is given to you is a subgroup H. And there's a natural question that you can ask. You take this representation of G and you restrict your attention to H. You restrict this map. So you have a map to GLNC, homomorphism. You restrict that map to the subgroup H, which is given to you. So that will be a sum of irreducible representation. That will be a representation of H because you have restricted your attention to H. And you can write it as a direct sum of irreducible representations of H. And you can ask which irreducible representations of H will appear in this restriction of pi to H. In particular, so this is a very wild question, so to say. I mean, the There's not much given to you, some arbitrary representation, arbitrary subgroup. How do we know what the restriction is? It's not easy, but we can ask a particular question. All groups have certainly one obvious representation, which is a trivial representation. The homomorphism to C star, GL1C, C star, everything goes to the identity element, everything goes to 1. So that is a trivial representation. So this 1 means a trivial representation, everything goes to 1, right? The trivial homomorphism. You can now ask in this restriction, does the trivial representation come? So this is a particular situation of this very broad question. So I started with a very broad question. Soon I am focusing on this particular question. Does the trivial representation occur? And if it occurs, there's a natural question that you can ask. If the answer is yes to this question, you can ask how many times does it come? Right? Does it come once? Does it come 1,000 times? Does it come 0 times? It doesn't come at all. All this may happen, right? So if yes, how many times? And this is the keyword of the title, distinguish. So distinction is with respect to this subgroup. So given a subgroup, pi is said to be distinguished with respect to this subgroup H. This is my notation for saying that in this restriction of pi of H, the trivial representation does come. It does appear. This is not equal to 0 is my way of writing that the trivial representation does come. So pi is said to be distinguished with respect to H if pi restricted to H contains the trivial representation of H. I hope the definition is clear. So it's a simple enough definition, can be introduced for any group, any subgroup with respect to any subgroup. This is slightly more generally one can define, instead of the trivial representation, you can take any character of H, and one says that pi is said to be chi distinguished with respect to H if in the restriction the character chi appears. Okay, so this is the definition. Now I said I will introduce this notion of a generic representation. So let me introduce that. That's a particular case of distinction. So what did the previous slide have? For distinction, you had a group G, you have an irreducible representation of G, you have a subgroup H, you are restricting your attention pi to H, and then you are asking whether the trivial representation comes or not, or the character chi comes or not. So there is what is called a Whittaker model, or a notion of a generic representation. This is a particular case of the previous slide, where I'm going to take a finite field E and a character of that. So an additive character of that field, meaning a field is a group with respect to addition, abelian group, and you take a character of that abelian group. And by this NNE, I mean all n by n matrices you have considered already. Now consider upper triangular matrices, right? They form a group. And now consider upper triangular matrices. Upper triangular meaning all the lower triangular part is 0. All the entries are 0. Consider all n by n upper triangular matrices where the diagonal elements are 1. Diagonal elements are 1. Okay. So in GL2, it will be 1x01, where x is anything from your field. So this is a group you can easily check, and you can define. So starting with this additive character, you can define a character of this group by, so in GL2, for example, you have 1x01 and send that matrix to psi of x, where psi is this, x is in E. If it is more generally, then you add the x12, x23, x34, these elements just above the diagonal. All those elements are from your field. Add all those, you are still in your field, and then you evaluate by this character that is given to you. So consider, so you can easily check that this is a character of this group of unipotent upper triangular matrices. You take this character, and now you take a representation of GL and E, n by n matrices, entries from this finite field E with determinant non-zero. And you say that the representation is psi generic if pi restricted to this group N, it contains this character psi. Then you say that it's psi generic. So this is nothing but, so in this particular case, you know, so you had in the previous slide 2 questions. When you restrict your attention to the subgroup, does the trivial representation come? And if it comes, how many times? So in this case, it's a famous theorem that the character psi, it may or may not come, If it comes, you call it psi generic. And it's a famous theorem that if it comes, the answer is 1. The multiplicity is 1. So put together, what it says is, when you restrict pi to n, this character psi will either, it may not come, but if it comes only once, not more than once. And this result is a 1962 result due to a very, very famous paper, Gelfand and Galois. Okay, so this notion of psi genericity is an example of distinction that I introduced in the last slide. And what are the groups and what are the subgroup? What is the group and what is a subgroup and what is chi? The group, big group G is GLNE. Big group G is GLNE, this group. Subgroup is group of upper triangular matrices with all diagonal entries being 1. And the character chi is this psi, which I defined here. So distinction with respect to this pair is another word, psi generic, or has a psi Whittaker model, and it plays a very important role in number theory. And so that's a basic example of this distinction. And you can see that this matrix, upper triangular matrices with ones in the diagonal, its determinant is certainly 1. So they are in SLN, and genericity can be defined exactly the same definition. Okay. And instead of GLNE, more generally, there are these finite groups of Lie type. The basic example is GLNE. So F is a finite field of Q elements. And you can take E FQ square. So the quadratic extension of F, degree 2 extension of F. That's a field of Q square elements. And you can take any connected reductive group. So a basic example to keep in mind is GLN. Another example is SLN. And you can take your big group to be the points of this degree 2 extension, and you can take the subgroup to be the points of F. F is contained in E, so H is contained in G. And for this pair, this notion of distinction is very much studied, a very important class of examples, and some history extensively studied by Roderick Gau. There's a famous paper of Gau in 1984. Important work by a Japanese mathematician, Kawanaka, Noriyuki Kawanaka in 1991. And Dipendra Prasad has a famous paper exactly on this topic, 1999. And George Lustig in 2000, another famous paper. So there are many more works. I'm just listing a few of those, a few famous ones. And so that's all that I will say right now about distinction for finite groups of Lie type. Let me come to, so in the first slide, I had 3 words, right? I had finite, I had local, I had global. Now let me introduce it for local fields, very similar. So G is a p-adic group, meaning you take a reductive group like GLN and take p-adic points, GLN-F, where F is a p-adic field, something like that. And take a subgroup H. And pi is an irreducible. I have added a word, but let's skip the technicalities. These are the correct kind of representations to study. Study of these representations is useful in number theory. So take the correct kind of representation of G. And pi is distinguished with respect to H exactly as before, except that instead of saying restriction, I have phrased it slightly differently. If the space of H invariant linear forms on pi is non-zero. Technically, you can write it like this. So these are the representation H intertwining maps from pi to the trivial representation. If this will be a vector space. If this vector space is non-zero, you say that pi is distinguished with respect to H. So what that means is there is a linear form. So a representation comes with, it's an action of the group on a vector space V. So I use, the same notation pi for the action and also for the vector space. So what this means is there is a linear form which is non-zero, non-trivial linear form on the vector space of pi. It's a linear functional, so valued in C. And so L of V makes sense where V is from the vector space. So you take L of V, pi acts on V. So you take action, pi is the action. So the group G acts on V, in particular the subgroup H acts on V, you take the action of the subgroup. So you take pi of H, H is from the subgroup capital H, you take pi of HV and you evaluate there. These two are equal. L of pi HV is LV. That's the meaning of saying L is H invariant. The action of H, it doesn't see. It's invariant under the action of H. And this happens for all V in pi and for all H in H. So this is the definition. Similarly, for a character, you can define chi distinction. So pi is chi distinguished with respect to H if instead of the trivial representation here, you write the character chi. So home H pi chi is non-zero. So what will be the definition in terms of this? There is a non-zero invariant form L such that L of pi HV is chi of H times L of V. Here it was trivial. In this case, there is a chi, so it will be chi of H times L of V for all V in pi, H in H. So that's a notion. And just like, earlier we had the notion of Whittaker model, here also exactly the same way. So I'm repeating most of these things. So as they say, if you see once, you may not get it, but if you see 2 or 3 times, you will get it. So it's a repetition in a different language, in a different setting. You say that the representation is psi generic if there is a non-trivial linear form lambda on the vector space of pi, valued in C, it's a linear functional, such that this is the same group of n by n matrices, upper triangular, diagonal elements are 1. So if you take any n there and v in pi, lambda of pi and v is psi n times v. So this is psi distinction. What is this character psi? This is the character that I introduced earlier. You take the elements just above 1, sum it up, and this is an additive character of the field E. So this makes sense. And this is the definition of psi generic. And you can write it this way. The psi NNE invariant forms on pi, that is non-zero. There exists a non-trivial lambda. And earlier we asked, we knew that either psi comes or psi doesn't come, but if psi comes, it comes exactly once. And a similar result, and there it was 1962 result of Gelfand and Graev. In the p-adic situation, in the local situation, exactly the same result is true. You can ask what is the dimension of this vector space, and this dimension is either 0, and if it is non-zero, then this dimension is 1. So always this dimension is less than or equal to 1. And there it was a result of Gelfand and Graev for finite fields, whereas in the p-adic fields, it's a famous paper of Gelfand and Karzan, 1971. As in the finite field case, here too, psi genericity is distinction, where the pair involved is N in E and the character that we defined, psi. Okay, and again for SLN, you can define exactly the same way, same definition. Okay, so now local distinction. So the distinction was, you have a non-trivial H invariant linear form, and this we could have defined for any p-adic group G and any subgroup H, but it becomes very interesting in this particular case. G, you take p-adic points of a reductive group, a group like GLNF, GLNE, and you take some involution on G, an order 2 automorphism. An automorphism of order 2 is called an involution. To take an involution and take the fixed points of an involution. So that will be a subgroup, the fixed subgroup of that involution. In this case, it's very important, and it has a lot of applications in Langlands program and via that in number theory, because there is this expectation, what is usually called Jacquet's philosophy, in honor of Hervé Jacquet, a very famous mathematician. And the expectation is that this simple notion of distinction gets connected to another important notion in what is called the Langlands program. H distinguished representations, a notion that we have already introduced, are there are various words used: lift, transfer, base change, functorial transfer, functorial lift, whatever. It's an important notion which I will not define. It's a bit technical, so I won't define it. But only thing that I will say is this is one of the most important notions in the Langlands program. It's called Langlands functoriality. Okay, so one of the most important notions in the Langlands program gets connected to this notion of distinction that I have defined, which was easy to define and therefore I had defined. Okay, these will be lifts from. So here is a group G and a subgroup H, but these lifts may be associated with a third group. Let's call it G prime. So this G prime is related to G and H, but not exactly G or H. It could be another group. It is another group most often. And a particular case of an involution where it's even more studied is what is called the Galois involution. What does this mean? You take a quadratic extension, right? Earlier we saw finite field FQ and the quadratic extension FQ square. Similarly, you take a quadratic extension of periodic fields, E over F. F is a periodic field and E is a degree 2 extension of F. So that the Galois element sigma is of order 2. And G is a group over F, and you can take the E points to be the big group and H points to be the subgroup. So it's a particular case of, so this is nothing but the fixed points of the Galois involution, right? You have sigma, which is a Galois element, non-trivial Galois element of Galois group of E over F is order 2. It's a degree 2 extension. Take the non-trivial element, sigma, and the elements of E which are fixed by sigma is exactly F. So this is what I mean by the fixed points of an involution. So take G and H. There are these conjectures due to Dipendra Prasad. I will not state it, it's a bit technical, but in particular, they address the question, characterize those representations which are distinguished with respect to H. Characterize representations of G which are distinguished with respect to H in one way or the other, and there's a precise recipe in this conjecture. It is conjectural. It's proved in some cases and not proved in other cases. It's a conjecture. So this is one part of the conjecture. And the other part is, I said that this is a vector space, and you can ask what is the dimension of this vector space. In the famous case of Whittaker model, you saw that this dimension is 1. If it is non-zero, then it is 1. And that was the result of Gelfand and Karzan from 1971. In this particular case, GEGF, you want to compute this dimension, and Dipendra Prasad's conjecture has a formula, a conjectural formula for computing this dimension. The only word that I will say here is, in the Langlands program associated to such representations, there is what is called a Langlands parameter, and these answers are these are conjectural answers, and these are in terms of what are called the Langlands parameters. So we are not, defining all these things, but anyway, having since you're attending this lecture, please keep the word in mind. And Langlands is a very, very famous mathematician, and many of some of the greatest results of the last century in number theory is due to him. So I had this third thing. Global is the word that I use for number fields. And maybe, let's skip some of these technicalities. So it's very similar. So there are all these things involved. I will only say that, there is this word called automorphic form, and we will not define any such thing. It can get technical, but let me just say that those of you who have seen the word modular form, it is a generalization of that concept. And since, this conference is about Srinivasa Ramanujan, etc., I think I should mention that the word modular form is something which is very much studied by Srinivasa Ramanujan. In fact, one of the most famous modular forms, all the students in KSOM will see it often because KSOM has people who are interested in these subjects, and KSOM does organize a lot of conferences, etc., in this kind of a topic of modular forms. And so if you haven't seen, you will see it soon in KSOM itself. One of the most famous examples of a modular form is the so-called Ramanujan cusp form, Ramanujan delta function. Okay, just a word here. So what I'm saying is these are, number theoretic objects, and some other technical things. And there is a notion of distinction over number fields also. But this is slightly different from the previous definition. The previous definition was there is a non-trivial invariant linear form. Here it's not about any non-trivial invariant linear form, but a particular linear functional is given to you. So you're integrating, so there is a invariant measure on the subgroup, and you're integrating with respect to the invariant measure. Therefore, by definition, this will be an invariant form. I am twisting it with chi inverse so that invariance is with respect to chi. So you're integrating, so you're averaging over the subgroup. And therefore, what you are going to get is certainly going to be invariant under the subgroup. But it's possible that this is identically zero on your vector space, on your space. This could be identically zero. If this particular invariant form is non-zero, then you say that it's distinguished. So a similar notion, but there's this deviation that you're not interested in any invariant linear form, but you are interested in one linear form that is given to you. And then you are asking the question whether this linear form is non-zero or not. So if there is at least one vector in your space, one automorphic form, so that when you evaluate on that, this integral is non-zero, then you say that it is distinguished. And whenever you have an integral, you have to check whether it's convergent, etc. And in this case, what is called a cusp form. So what is a Ramanujan modular form? That is an example of what is called a cusp form. And if you take a cusp form, this integral converges is something that is known. So in all my situations, I had a basic example in terms of the Whittaker model. So here also you have that. And so you have the notion of a global Whittaker model. So similarly, like my earlier character, you can define a character here, starting with an additive character of your starting with your number field. So there's an object which I did not, it was there in the last slide, but I did not stress it. Anyway, there's a parallel here. You can introduce a character here, and then you have the notion of psi genericity, which is exactly like my definition. So you introduce a linear functional, and if this linear functional is non-zero, and the linear functional is obtained by integration. So this is exactly similar. So as in the finite and local cases, exactly as in the previous cases, once again, psi genericity is nothing but distinction with respect to this pair. So for SLN also, it's defined exactly the same way. Let me do a bit more history on the most well understood case, which is when your reductive group is the group of group GLN. So GLN E is n by n matrices with determinant non-zero. E over F is a quadratic extension, and then you are taking GLN E, GLN F, and this is one of the most well understood case. And some history on this slide, some early works. There's this paper of Jacques and Lai from 1985. This is the paper where this theory started. So though my year is 1986, I think this paper was first, and this got published in 85. But this is the very first paper in the subject. It's by Harder, Langlands, and Rappaport. And this is the paper that introduced the notion of distinguished representations and connected it to the notion of base change and connected it to various other things. In fact, I must say that this paper is a paper in algebraic geometry. The conjecture that this paper addresses and solves in a particular case is a conjecture from algebraic geometry or arithmetic geometry. There's a famous conjecture called the Tate's conjecture. And in order to address that problem in a particular situation, they had to introduce this notion of distinguished representation. That's how it started. This mathematician Yuval Flicker, and he had a series of papers. By the way, there are many more recent papers, so I am only referring to historical papers. So I cut my date as 2000. So I am referring only to papers below 2000 from the last century. And he had a series of papers, some of them mentioned here, 88, 91, 92, 93, all on this topic of GLNE, GLNF distinction. There's a famous paper of Jeff Hakim, which was his PhD thesis. He was Herb Jacquet's student of Jacquet, 1991. Dipendra Prasad had a series of papers, just 3 years I am naming here, many more papers on this topic. But I'm going up to 2000, 2001, so 92, 99, 2001. There's a paper of Flicker and Hakim together, 1994. There's a very famous work of Hakim and Murnahan, 2002. And some of the later works include a paper of Anthony Cable, a paper of mine with Anthony Cable and Rajat Tandon, who's my PhD advisor at the University of Hyderabad. That's 2004. Another paper with C.S. Rajan, who lectured not yesterday, but day before yesterday in this conference in TIFR. So we have a work in 2005, another paper in 2008. And then there were many significant advances by Nader Matranj, who has a series of papers, just 3 I am naming here, 9, 10, and 11, and Omer Offen, 2011. So some of the works that I'm going to, some of the new results that I'm going to say later are, I said, joined with this mathematician, Nader Matranj, and also with the papers. So they also come up in the slide. So in particular, some basic things here. So to an irreducible admissible representation, there is what is called a central character associated to it. So what is a central character? The group that you're considering is GLN-E. And what is its center? Center is scalar matrices, right? Center of this group is scalar matrices. And the scalar matrices will act by a character meaning a one-dimensional representation. And what one can see is, so every irreducible admissible representation has a central character, a one-dimensional representation naturally associated with it. It's an action of the center of the group. And distinction implies that the central character is trivial on the ground field, on F star. That's easy to see. So here is a proof. You take any A from F star and any vector V from your representation space, and the L of V is L of pi of HV for any H and H. This is what distinction means. And in particular for H, you take the diagonal A, etc. The scalar matrix with A everywhere. And if A is from F star, this is from the subgroup H. So L of V is L of pi of HV. So this is true. And by the definition of the central character, if you have such a thing, then if omega pi is a central character, then omega pi of A comes out. That is the definition of the central character. So this will be omega pi of A times L of V. And there is an L such that L of V is non-zero, right? So choose such a V so that this is non-zero. So you can cancel L of V on both sides. So omega pi of A equal to 1. So that's the meaning of trivial central character. And a famous result of Flickr, one of the papers that I mentioned in the previous slide, distinction implies what is called conjugate self-dual. What does that mean? The Galois group is a group of 2 elements. So let me denote the non-trivial element by sigma. And you can define this representation pi sigma. Given pi, you can define pi sigma by pi sigma of on the group element G. So G will be an n by n matrix with entries from E. And you just define it as the action of pi on the element G sigma. And what is G sigma? You have an n by n matrix. Each element is from, each entry is from the field E. To each entry, you apply sigma. So you will get a new matrix and call that G sigma. So like this, you can define the representation pi sigma. And to every representation, there is a dual object, what is called the contragradient representation, right? A vector space has its dual vector space. Similarly, this representation has a dual object in this category, which is called the contragradient representation. And conjugate self-dual means these two representations are isomorphic. The contragradient of pi is isomorphic to the conjugate, the Galois conjugate of pi. There is this isomorphism. So it's a famous result that if you have distinction with respect to this pair, then the representation has this property that its contragradient is isomorphic to its Galois conjugate. Okay. And there's also multiplicity 1. So earlier, I mentioned in the context of Whittaker model for finite fields, I mentioned this result of Gelfand and Grayer from 1962. For periodic fields, I mentioned this result of Gelfand and Karzan from 1971. These are all examples of multiplicity 1 results. You have a certain vector space of invariant linear forms, and you are asking what is its dimension. And a multiplicity 1 result would say that, look, in this particular situation, the multiplicity is at most 1, meaning the multiplicity is either 0 or 1. And in this context also, such a result is true, and that is due to Yuval Flicker, 1991. So it's stated here, if you take GLNF invariant linear forms on the representation pi, that forms a vector space, and it is at most one dimensional. It's either 0 or 1, the dimension. That's also true. Now let me come to the new results. And as I said, the GLNE, GLNF is very well understood. We know many things. SLNE, SLNF is a bit subtler. And why is it so? Because as I said in the very first slide, it's not one representation that you look at, but a packet of representations together you have to look at. In some sense, this is analogous to, so those of you who have studied finite group theory and representations of finite groups, one of the first class of examples that you would have looked at would be permutation groups, SN. And that representation theory you would have studied. You might have also looked at alternating groups. And if you have seen these things, you must have seen that it's a bit more subtle than studying representations of permutation groups. Alternating groups a bit subtler than permutation groups. It's something similar which is happening here. And the main point is you have to look at a group of representations together. That's why it's a bit subtler. And this happens naturally in the Langlands program. Let me illustrate for finite fields what one of these points is, why one is considering a group of representations and not a single representation. So here is, one of the basic examples, SL2FQ, where Q is 3. So it's SL2F3. It's a group of order 24. And you can write down its irreducible characters. So I think SL2F3 has 7 conjugacy classes, and therefore there will be 7 irreducible representations. And these are 7 irreducible representations here, 1, 2, 3, 4, 5, 6, 7. These are the dimensions of the irreducible representations, 1, 1, 1, 3 representations of dimension 1, 3 representations of dimension 2, and 1 representation of dimension 3. And these are the conjugacy class representatives. You can write down the character values. So what happens is, so I can't highlight just this much, but what happens is there are matrix elements which are not conjugate in SL2F3, but they become conjugate in SL2F3 bar. For example, you can take these two matrices in SL2, 1, 1, 0, 1 and 1, minus 1, 0, 1. Simple linear algebra, you can check that these two matrices are not conjugate in SL2F3. They are not conjugate by an element of SL2F3, but they are conjugate by an element of SL2F9. So in particular, SL2F3 bar. So such elements, certain representations take different character values. So here is something and here is something else. Here is something and here is something else. So such things, when it happens, it's better to study both these representations together as a packet, as a group. And this notion can be more rigorously done for finite fields. And this is the notion for finite fields. You can do the notion for periodic fields. You can do the notion not like this, but in some other way over global fields, etc. This is what gives rise to the notion of a packet, an L packet. So basically what all I'm trying to say is there may be group elements which are not conjugate over your base field, but they are conjugate over an algebraic closure. And you would ideally like to have your representation taking the same values on those elements. But if it doesn't happen, you combine those representations together and study them collectively. So that's a packet. A very vague introduction to L packet from a basic example. Okay. So the question is, if naturally what you are getting is a packet, whereas the notion of distinction that I introduced is for a single representation. So inside a packet, there may be representations which are distinguished, and there may be representations which are not distinguished. And you would like to probe inside a packet. You want to go inside a packet and focus on each representation individually. So collectively, you know something. Now you would like to know something individually for each representation, whether something is distinguished or not. So how to probe this? And the conjectures that I mentioned earlier, due to Dipendra Prasad, a part of that conjecture, so conjecture has many parts. There's a famous multiplicity formula, etc. But one part of the conjecture would predict which representations inside such an L packet probably are distinguished. In particular for SLN, let me state, more generally, you need a little bit more. So SLN, it would say, so I have introduced this notion of genericity, psi generic, where psi starting with an additive character psi of your field. And the conjecture in particular for SLN would say that if you have a local generic L packet, and assume that your L packet has at least one distinguished representation, then the conjecture says what exactly are all other distinguished representations? And what is the answer? The other distinguished representations are precisely those representations which are psi generic, a notion that I introduced earlier, for a non-degenerate character psi of NE upper triangular matrices with ones on the diagonal. But this character has a property that on NF, when your entries are from the base field, this character should be trivial. So it's a non-degenerate, non-trivial character of this group, which is trivial on the subgroup. With respect to such distinguished characters, ask the question whether your representation is generic or not with respect to such characters. And the conjecture would predict that for SLN, the prediction would be that such characters, such representations, which are psi generic for this kind of a psi, psi which is a character of E which is trivial on F, a non-trivial character of E which is trivial on F. With respect to such psi, if your representation is distinguished, is generic, then those are distinguished for SLNF. Okay, so there's a very precise recipe, very precise prediction. And so the next slide is the new results. And so let me call this statement star. So star is the statement that the conjecture is true. Okay, so star is this statement, and let me state some results. These are the results joined with Nadir Matranj and Deependra Prasad. Some results with Nadir Matranj and some other results with Deependra Prasad. And results involve finite fields, results involve p-adic fields, results involve number fields, global fields, but all for SLN. So in particular, this star, this statement. So let me go through some of the results and then I will stop. So star is true for n equal to 2. SLN you had, no? SLNE, SLNF is what you had. And when you take n equal to 2 and when E over F is p-adic, this is true. And this is 2003 result of with joined with Deependra Prasad. So A is my name and P is for Prasad. And this was when I was a postdoc in TIFR with Deependra Prasad. And n equal to 2 in the number field case. In the global case also this is true, star is true. And this is a 2006 result again with Deependra Prasad. Any n it is true in the p-adic case. So this was n equal to 2 p-adic case. And this is generalized now to any n but p-adic. And this is more recent, 2018 it got published. Maybe the result is from 2016, end of 2016, got published in 18. And this is also with Deependra Prasad. So 2018, we have proved Prasad's conjecture for SLN. We proved all parts of the conjecture. I'm stating only the star part because that's where I have results in other cases. Even the other parts of the conjecture is solved for SLN now, and that's the same paper in 2018. And n equal to 2 finite field case, you may be surprised that p-adic case is done in 2003, finite field case in 2018. But sometimes it happens that even if one can do it much before, one might not have looked at it. So it's for some such reason it is written down only in 2018. That's why it's more. It appears more recent. So it comes in 2018. N equal to 2 finite field case. And any n, not all the finite case, but what is called a subclass, cuspidal case. This is also done in 2018, the same paper. So we do both p-adic and finite field case, but finite field case is done in all generality only for n equal to 2. For any n, there is a further assumption. This is some technical further assumption. But any n general case also we have done, that is much more recent. It got published only now, this year. And this is NEN. You don't need this assumption, general case, general finite case, and this is with another matrix, M for matrix. And NEN number field case also is done, and I have put 21 because it's a preprint from this December. So hopefully it'll get published next year, or maybe 22. I have to make it. Sometimes, again, students are there. It's a very first batch of integrated MSc, PhD students. So you have to do your 2-year MSc, and then you will start your PhD program. And in mathematics, getting new results, etc., take a lot of time. So you are probably thinking of writing your first paper after, I don't know, 4, 5, 6 years, depending on various factors, including good luck. And yeah, so this is one thing in mathematics that, papers take a lot of time to get refereed and get published, etc. So I will change the year accordingly. So any n number field cases also done. A remark that in this preprint we consider more than generic representations, but that's a technical remark. Anyway, this is a talk intended for a general audience, including integrated MSc PhD students. So just a technical remark I will leave on the slide. I think it's a good time to stop. I have 10 more minutes. I have 8 more minutes maybe. I have a few more slides also. But in this slide, what I have done is I have illustrated a proof of this case. But I think maybe it's not very proper for me to get into the proofs. On the other hand, it's also being recorded and it will be there on YouTube, etc. So as a compromise between going through the proof and not doing anything at all, let me just go through the slides so that on the video it is there. But as far as the talk is concerned, let's say the talk is over. I will just go through the slides so that if someone is interested, one can check the video. But since this is a talk meant for a general audience, let's consider the talk to be over. So this particular case, number 5 here, a proof, the summary of the proof is illustrated in the next 3-4 slides. I'm not going to read it out, but let it be there in the video. So the key word here is what is called Clifford theory in finite group representation theory. In fact, it's related to this method of little groups of Wigner and Mackey from this famous book, Representation Theory of what is the word? Representation Theory of Finite Groups, the famous representation theory book of J.P. Sayre. Okay, so this is a quick indication of how that particular case is proved. So it's an inductive argument. Okay, I think I'll stop the lecture here. Maybe I'm ending 5 minutes earlier.
Thank you so much, Professor Ananda. And really, it was a very illuminating talk, I would say, even for this integrated MSc PhD students. At least they could see that how the problems are being considered for various cases. And finally, you arrive onto the final cases for general degree extensions. And then the piece of as a suggestion or advice that Ananda gave to all of you, that, it's not that easy to get into research. You need a lot of patience, a lot of hard work, and it is all of you are there. So thank you so much, Ananda. And now it's time for the audience here first, that if you have any queries or questions for Professor Anandavardhanan. So Ananda, Professor Krishna Kumar is also here.
Yeah, I just saw. Only now I came, stopped the screen sharing. So nice to see you once again. Yeah.
Before I go to the chat and other things, maybe Professor Krishna Kumar will just congratulate you because he was not there at that time.
We had a video call.
Well, Anand, it's nice seeing you talking again. I think the last we met was in Mysore, Bhubaneswar, sometime when you came and gave some lectures. Yes. The topic is too technical for me, but I really see the spirit in that, and I should think that the students should get inspired by listening to him. Incidentally, Anand is a local boy in the sense that he hails from Calicut, around Calicut, near the university. And his father is a very great scholar of Sanskrit. And he's also a colleague. He was a colleague of mine at Calicut University. He was in the Sanskrit department. So I knew him from when he was a little boy, right from those days. I mean, the family is very close to our family. So anyway, it is really wonderful. I mean, when he came to Bhubaneswar, he spent some very nice time in the campus there. Okay, Anand, wish you all the best. And I'm very happy to see that your work is really progressing in a good pace. Thank you very much.
Thank you so much. Maybe I will also just add that Professor Krishna Kumar mentioned our close connection from my nursery days. And in fact, I wanted to do MSc in Calicut University. And it's on his advice that I went to University of Hyderabad. So my father asked him that he would like to be here because I'm from that campus and I wanted to be a local student. But Professor Krishna Kumar told my father and me also that better to go outside to see the world. That's how I ended up in Hyderabad and worked with Professor Rajat Tandon. And it's Professor Krishna Kumar who introduced me to Professor Rajat Tandon when Professor Tandon was visiting University of Calicut. And so I mentioned this here because I heard from Pranav yesterday that in the integrated MSc PhD program, there are students from all over India who have come to this local city of Calicut. And I guess it's very similar in spirit. Just like, I got the advice to go outside, for you to come here also is in the same spirit. It's always good to go around. Thank you so much.
Thank you so much, Ananda. Thank you so much, Professor Krishna Kumar. Please, this piece of information certainly is a real encouragement for the students who have just come out from the family first time, leaving. So it was really wonderful, Anand. Now I'll go to the questions. If they're in Zoom, whoever wants to ask any question can unmute them and ask Anand if you have any question. Yeah, so we move into YouTube chat. If Srijit can pass on in case there are any queries.
No, sir, there are no queries here.
Okay. So thank you so much, Anand. And really, we are eager to see you here. Not 3-4 months, as soon as the situation normalizes.
Situation improves, yes.
Here and here, we want to see you. Yeah. So bye-bye, Anand. Take care, and we'll be really waiting.
Yeah.